Hi, good morning. Thank you for joining me here in my shop. Today is the last day of March, March 31st, 2024, in case you don't know what year it is. And I'm going to start out by talking a bit about the odd experiences I had with this radio yesterday and this output tube. This is the original output tube. This is a replacement here. So what I did was I did the standard thing, check the grid to see if it's positive. Oh, a little bit positive. Change the blocking capacitor to stop the leak and stop the positivity on the grid of the output tube. But when I change the capacitor, there's still some positive voltage sitting on the grid. If you measure the voltage from the grid to the cathode, you can see that. I'll take that back. If you measure the grid to ground, you can see the voltage sitting there. Where's it coming from? Still leaking through a new capacitor? I don't know. So I changed tubes. This is the replacement tube. The voltage is still there, but it's much less. Or it's less. What voltage is this? Now, it's a very small voltage I'm talking about. 0.2 volts positive. What's that from? So I'm really not sure yet, but I was reading up on a tube effect called contact potential or contact voltage. Exactly what that is, I couldn't find, although I found an article talking about it. So it's a voltage that I guess was measured in the early days by the early experimenters. Somebody discovered it, named it contact voltage. Maybe they in their heads have an idea of how it develops. I don't know. Electrons fighting their way into the grid. I don't know what it is. But it's there in any case. And it wouldn't be electrons fighting in because it's going positive a little bit. Or the capacitor I put in does leak a little bit. I don't think so. I don't think it has any propensity to leak at all. So it could just be a tube factor. Now when I change tubes, that little voltage changed. And if it is the contact, I'm doing the quotes thing, the contact voltage thing, then it might vary from tube to tube. I believe, I'd have to read this again, that a tube with a weakened cathode can show a higher contact voltage. And that seems to be the case. The tube that tested weaker on the tube tester is the one that has a slightly higher voltage I'm reading on the grid. So I don't know if any of this is correct or not. You can read up on contact voltage. Maybe there's a much better article out there than what I was reading about this that really gets down to the actual atomic effects that are occurring, that are generating this voltage or this pressure that you can measure with a meter. Okay, but that aside, it would appear to me then that this is just a normal thing that happens in tubes that you never normally test for or recognize or spot, and is overwhelmed and washed out to sea by all the other voltages and currents that are taking place in the radio. So in the end, it's of no consequence, I believe. Although, interestingly enough, you could tell a tube was weaker if you found the contact voltage higher if you knew how to measure it. Now, I've never seen a tube tester with contact voltage anything on it, so I really don't know. Maybe if I learn some more, I can tell some more somewhere down the road. So what we want to do today, what do we want to do today? Today, I think we're going to continue with some capacitors here. The capacitor I did take out and tested pretty good. Not terrible. There we go. So, this is the capacitor I've changed. So there's a big guy here. And it looks like the end seal has given out here. And there's another big guy over here. He looks pretty good. In good shape. So why don't we go after this one? This is the biggest capacitor in the radio. Can I read the value on it? I cannot. Oh, look what it's doing. So it's connected to the chassis here. So this is the chassis quieting capacitor. Usually there's a resistor, or there could be a resistor in parallel. That last radio I did, this capacitor was a Philco special capacitor. I know a lot more about that capacitor, by the way, and if you watched that video, you saw me tear it all apart and all that kind of stuff, and then pronounce no coil. Yeah, no coil, but it still is a special capacitor, because I thank you for someone who sent me an article that details exactly how it was made. You might remember, if you watched that video, when I peeled the capacitor apart, I found 2 tabs on the ends, and I think I said, oh, that's unusual. There was just these metal tangs or tabs that were on the ends. That was the hint right there. So anyway, I'll talk more about that some other time. Let's deal with this. So we want to find out a little more about this. Let's look at the schematic and see what it says. So I apologize if I'm talking about other videos and radios and you haven't watched those videos and don't know what I'm talking about, but I'll stop and get back to this one here. So we're looking for a capacitor that's connected to the chassis. Now this denotes B minus, and this symbol denotes connections to the chassis. So there's one here, one here, one here, but I'm looking for one stuck on the end of a capacitor. Oh, look at that. That's an important thing to spot, that there's a connection to the chassis on the isolated part of the speaker here. Just good to know. Show me, here's a capacitor, and no, that's the B minus. That's the B minus. Where are, so see these connections are going up to pin number 1, and they actually connect to the shell here. Well, it doesn't look like it, does it? It looks like pin 1 is this. Pin 1 is this, but it shouldn't go into the suppressor. It should be more like that. And here, oh, that's interesting. This is done differently. 12SA7. They're showing the suppressor grid connected directly to the chassis. In this one, the suppressor grid is connected to the B minus. I gotta wonder about this. That's interesting. Okay, a little aside, but normally you see what they're doing. This represents the metal shell on the outside of the tube, and it's connected to the chassis, because you just don't want pieces of metal, isolated pieces of metal, hanging around your radio. They're going to cause you trouble. Here's the thing I'm looking for crying out loud. Yeah, I'm looking all over the place for this. So you see, here is a capacitor with a resistor in parallel with it. Oh, we didn't see the resistor just yet. This is quite common, how this is done. So, point to a very large capacitor. Chances are it's leaky a little bit, and a leak here could be dangerous. In a radio of this sort, with this kind of plug, you don't know, it's 50% plugged this way, 50% plugged the other way. Half the time, the B minus is going to be at 120 volts above ground. Dangerous. And then you've got this chassis connected to it through these components. These components are good. You're going to get only the smallest of shocks off this. You won't even feel it necessarily. You can get what's called a brush shock, and also you can get some funny sparking if you drag wires on the chassis, and you might get some funny sparks. But not enough current's going to flow through here to cause any real harm, unless this capacitor is shorted out or is very, very leaky. You may get more current flowing through here, maybe more current flowing through your finger and out your toe, and maybe you're going to get killed by it. So we don't want that to happen. We need to check this capacitor. It's a safety issue, more or less. Great big capacitor there. Okay, let's do that. I think it's time for me to develop my my skills here a little bit when it comes to the hot chassis radio and the like. Now I have an excellent instrument here to help with testing the situation here, and that's this guy. This guy is able to read very small leakage currents that might represent the current leaking through this capacitor, and that could be a dangerous current. So in the fact that you touch the chassis, you can get a shock, particularly if you're touching this and something else, whatever that might be. Maybe another radio, maybe, who knows. So there is a concern here about how much current is leaking through a capacitor like this, and is it enough to make the situation dangerous. So what I want to do is a before and after test. I want to test the radio in its current state with this capacitor in place, get some idea of what kind of current leaks through it onto the chassis that might shock me or somebody else, and then change the capacitor with a new one, and then repeat the test and see what happens. Now, I just did this with a tube and ended up discovering something quite obscure. So I'm always open to learning new things, and I'm also very open to having my paradigmic thoughts corrected. Paradigmic, is that a word? So let's look at this device, and we're going to look at the instructions for this device here, because I don't make a lot of use of this. I like the dim bulbs to protect a radio. You can use this device to get my glass bird out of there. Hey, look at this. glass bird's in here. I'm going to pull this plug out. Okay, so like I say, we're going to read the instructions on how to do this, and but here's the labels on these buttons. This says line, so now we're reading the incoming voltage to this device, and it says it's 121. Do you want to believe that? There's 121 volts in a regular outlet. Here, this is the output. The output is controlled with this knob, so you can crank it way down and start your device with 40 volts if you want, or you can start it with higher. You can turn it higher if you want, but I usually leave it set so 120 is coming out. So you can see how you can have a low input voltage, 110 volts, and you can still get 120 coming out of this if you really want to get that voltage. Where would you get it from otherwise? You need something like this. So line. Actually, I've got the two of them set almost identical now. So it's got a couple more settings here. One is 0 to 1.5 amps, 0 to 4 amps, so you can read the amount of amperage being drawn through this, usually because of some project on my bench. But here's where things get interesting. Now here it says leakage, high side, low side, with a place to plug in the probe. I have to find the probe now. This is what we're going to read about and we're going to use. We're going to read this meter. We're going to find out how much current is leaking into this chassis. We're going to find out if it's a dangerous level or not, because there is some values I found in a document. And we can make some judgments about the condition of the radio. I can make a change to it and then make those same measurements again and find out, yes, this worked. No, it didn't work. Oh, here's something I never knew about. That's kind of where we're going with this. So let's take a look at the instructions here. So there's an awful lot said in here about this device here, but let's just go down right here. This is just the instructions on how to use it. So let's go through here. Leakage current cold check. Unplug the AC cord and connect a jumper between the two prongs of the plug. I've never done anything like that before. Turn on the receiver's power switch. Measure the resistance value with an ohm meter between the jumpered AC plug and each exposed metallic cabinet part on the receiver, such as screw heads, connectors, control shafts, etc. When the exposed metal part has a return path to the chassis, the reading should be between 240,000 ohms and 5.2 megohms. I know where the 240 comes from. That's the value of the kind of resistors you find paralleling the big capacitor. I think in here it's 220. Where they get the 5.2, I'm not sure. When the exposed metal does not have a return path to the chassis, the reading must be infinite. So if that big capacitor and its fellow resistor were not in the radio, then this is what we would find. We'd take this reading and find out there's no connection between the chassis and the stuff inside the radio. Let's do this one. I've never done this. It's pretty simple. Maybe I've thought about these kinds of things, but never, like a lot of things, unless you do quite a few of them, you don't have you don't have any instinct as to what the result is supposed to be. But here they're telling you what the result should be. So for an ohm meter, we're going to use the digital meter. So there's no doubt about anything. Okay, so it did say between the plug here and all exposed metal. So what are they talking about? Well, normally this chassis is not exposed. It's inside the cabinet. What is exposed are these metal knobs sticking out, maybe some stuff on the back, screws going in from the bottom. They could be touching metal. There's a plate that goes over here, and screws go into the plate, and who knows? Well, wasn't there some paper inside that thing? What did I do with it? I put it in the cabinet and put it away. Okay, we won't worry about that. Stay on track, Jim. Focus, man, focus. So here we go. So we're going to read from here to the chassis. You may want to take a guess as to what we're going to get. I think it's going to be 220. I killed it. Yeah, a little too excited there. Let's tip it right over like this. Two 227, 220. So that's the resistor, which we haven't found yet. Somewhere there's a 220 resistor also connected to the chassis. Where are you in here? So 220 would be a red. Yeah, look, here's a 220 right here. Red. And how does this end up being in parallel with that? That's a good question. I'm just tracing some wires quickly. I don't see it. Over this side. I don't see it. I don't. So maybe this is some other resistor. Happens to be the same value. There's a lot of, in this radio they've made a lot of connections just floating. Like this is just floating out here. It's pretty rigid though, but it's not on a terminal. It's a little unusual. I don't know where that mystery resistor is. Unless I just didn't sort things out here, and in fact this is it. Or am I being totally fooled? No, it did show it on the schematic. But you would think it would be right here, like going right across. In some cases they do that, they take the resistor and they lay it right on this capacitor, and then they put the leads onto the leads of the capacitor. This becomes a little unit, sort of. They can install it then. But not here, unless it's hidden. I don't see it. What did we get here anyway for reading? We got the 220. We got the 220. What am I saying? One side of this grounded. So it looks like this is a grounded terminal, even though I don't really see how it's grounded. I don't get it. But that's a pretty good zero there. So somehow that's becoming grounded in a way I can't seem to spot. This large resistor here. And the color is, I can't see it, black-red. This is probably brown, black-red. So this is a 1,000 ohm resistor here. Is it really? That's 1,000 on this scale. The only reason I'm checking this is because it's right here in front of my face, and I've got the ohm meter in my hand. So it's 1,100 instead of 1,000. That's probably fine. So with that resistor there, that's the main control on the rate at which current is going to leak into this, into here, I would think. I would think if I nip that, we would then see only the capacitor. And for the sake of the experiment I'm doing, that's what I'm going to do. I'm going to nip that resistor, even though it appears to be just fine, to get it out of the circuit, and leave only the capacitor behind. I'll just solder it back later. There's lots of excess lead here. It'd be easy to do. Don't really need this clip lead. I could put the clip lead in to mark the terminal so I wouldn't forget, but I'm not going to forget. I promise. Promise I won't forget. Now we repeat that test. Now we're seeing just the capacitor. So let's see what happens. I'm going to use a clip lead here because holding the meter on is just a little shaky. difficult. Okay, watching the meter now. Well, that's kind of interesting. I cut this resistor. Wait a minute, it fell back. How did that happen? Did I knock it? I cut the resistor and we still have the same voltage. This isn't the right resistor. There's got to be another one in here somewhere. Oh my God, they didn't stick it right in the capacitor, did they? Have I got another one of these weird special capacitors here? Oh my. Let's just put this on and off. Oh, it does make a difference. Sorry, I got my hand in the way there. Get my hand all over everything, so let's not do it with my hands. I perspire. My hands perspire a lot when I'm in here working, and they're really, really conductive. And it's really... I'll tell you a story about that in a second. Okay, watching the meter. Not doing anything. So this resistor has nothing to do with... Where's the mystery resistor? Let's cut the capacitor right out. Because I'm going to replace it anyway. We'll just cut it here. Okay. Somewhere there's a resistor in here I can't find. Underneath something, hidden away. It's got to be in here somewhere. Okay, but you can see we cut out the capacitor, made no difference. So the amount of current leaking to the chassis is really controlled by that resistor and this capacitor. If it was adding to it, it was adding a tiny, tiny amount of no consequence. So does that mean this capacitor is safe to leave in here? You know, it probably is. I mean, there's always a chance it's going to short out, it's going to fail somehow, but the chances are fairly low. Probably could just leave it and not worry about it. Okay, so what you're going to do next, kind of repeat all this, but using this instrument to get me familiar with using it. That's the idea here. I'm sort of self-training this morning. Okay, well, I spotted that resistor. Pretty hard to see it because of the funny angle it's on, but it's right there. I'll put the close-up camera on it. We can take a look at it. Red. So there it is. Now you can see, well, I can put a little more light on it here. That should be red, yellow there. You can't really see the... Hey, my lights aren't on here. Can't really see the other red, but no doubt that's red, yellow there, which would be 220K. You can see the one side is soldered. What they've done is they've soldered it to here. This is a rivet holding the tube socket to the chassis, and they've used that rivet. Rivets aren't the best for this kind of thing, by the way, but they've soldered it there, and the other lead comes up, and disappears. Goodness knows where. It goes to this busy terminal here. Just whacked my head on another light here. Okay. So you can see the busy terminal, all that stuff hooked up to it. That's a B- connection point. One of those wires is the resistor. So we know the resistor's testing 240. It's supposed to be 220. That's nothing to be concerned about. How can we test the effect of this capacitor? I mean, I've cut it out of the circuit already. We'd have to cut this resistor out. Or we're testing the capacitor on its own outside the circuit. But I really want to get a feel for this. So I think I'm going to solder this capacitor back. I'm going to solder this other resistor back. Then we're going to cut this one. Because, you know, nice, well, let's see. Can we get at it here? Don't move stuff too much. Could probably get at it there. I can always replace it. It's no big deal. That's the experiment. Okay, let me solder back those parts, and then we'll perform the test. Okay, I have the radio back in its original state again. I've soldered this back, resistor's still in, so everything is just the way it was. And we're going to look, and that's why I've performed this resistance test. I got a reading of 220. 220 indicates this resistor is there. This resistor's there. That's about all you can get from that test. And does that make the radio safe? Let's look at the instructions for the next part of the test. Okay, so we're reading here. Leakage current hot check. I guess this is the cold check. Hot check. Plug the AC cord directly in the AC outlet. Do not use an isolation transformer for this check. Okay, so I have an isolation transformer. I'll have to do something different here. Leakage current hot check. Well, wait a minute. Aren't you supposed to plug it right into that Sencor power right device? But it says don't plug it in with an isolation. Okay. Do not use an isolation transformer for this check. That's weird. That's almost like saying do not use the device you're reading the instructions for this test. Connect the 1.5 1000 ohm, 1500 ohm, 10 watt resistor in parallel with a 1.5 capacitor between each exposed metal part on the set and a good earth ground. Hey, wait a minute. This isn't how you... Servicing hot chassis, performing tests with your power array. Use an AC voltmeter. Check exposed. This is how you do it without the device. That's what this is. This is showing, I think, because I read this over here, why don't most servicers perform the leakage test? And the answer is it's difficult, and they're showing it here. So they're trying to make a big deal. Yeah, you try to do this on your own, look what you got to do. But you can use the device. So it must be on the next page. Okay, sorry I'm dragging you all through this. What causes leakage? Oh my gosh, look at all of this writing here. What? What? Attackers might be trying to steal your information from Vilvegrinon pics. What the heck is this now? Don't click that, that's for sure. I'll use this button up here. Okay, don't have any idea what just happened. Let's try it again. I just clicked this page. Something strange happened there. I don't know. Was that an attempt to get me to let somebody into my computer? I don't know. Okay, moving on here. Yeah. So what caused it? We were reading all this. To make a safety leakage test with your PR75, simply plug the chassis into the power right, plug it in there, and touch the probe to all exposed. Well, that's pretty much. That's pretty easy. What's all this talk then? Next page. Okay. The push button of the safety leakage probe is depressed when the actual value of leakage current is to be read. It has a button, but when you push the button here, it doesn't seem to go anywhere or do anything. So we'll find out. What's all this? The leakage test, it's fast and simple. Simplifies safety leakage test because all circuits are internally referenced in the isolated output of the PR. Whenever you have to the leakage test, you can under test. Other procedures require a direct connection. Yeah, no. Once again, they're just trying to sell this test. Here we are to perform the leakage test. Finally, plug it into a properly grounded 3-wire AC outlet. Okay, it's been done. But yeah, I don't know, because I have my PR57 plugged into another isolation transformer. It's double isolated in my shop here. Still going to work? I think it's going to work. I think it's still going to work. Push the AC volts output push button and adjust the volts control for 117. Establish a 117 volt reference for uniform test results. So they've calibrated everything based on the fact that it's putting out 117 volts to start with. 117. Press the high side leakage button, plug the safety leakage probe into the probe jack, touch the probe to every user accessible piece of exposed metal, including screw heads, everything you can think of. Read the leakage on the microamp leakage scale. To read the true leakage current, push the button on the probe. Why? Push the low side leakage push button and repeat the test to all the same points. The safety leakage probe has a switch which places a current limiting resistor in series with the test circuit. The resistor is bypassed when the button on the probe is depressed. The resistor limits the amount of current to prevent the meter from pegging. So basically you don't know what it is you're about to do with the meter, so the meter is very insensitive to start. But when you want full sensitivity, you just push the button on the probe. This condition occurs at the point being tested connected directly to either side of the AC line. Oh, I see. So the problem is you're looking for a small effect, but some of these radios have a directly connected AC power line right to the chassis, and in that case you're going to get a big blast on the meter. So to counter this problem, they've put a button right on the probe, and you start out with it being very insensitive in case you encounter this 120 volts. You don't want to blow the meter. Any test point that reads close to full scale with the button in the out position is connected directly to one side of the AC line. If, for example, the meter reads full scale when the low side button is depressed, there is a direct connection between the common AC line. This is the side of the polarized plug, larger connector. Leakage readings which are less than full scale indicate there is a leakage pass, but not a dead short to the point being tested. Simply press the button on the whoops, what happened there? Press the button on the safety leakage probe to read the actual leakage current present. And then page 4. This is quite I think it's fairly straightforward. How much leakage is bad? This is what I'm concerned about. The chart, figure 4, shows the effect of electrical shock on the human body. You may be surprised to learn that the most likely range of a fatal current is between 30 and 250 milliamps. This is the area where breathing and the heart are most severely affected. The chart is based on a person weighing 150 pounds. Smaller people, especially children, are more susceptible to shocks at lower current levels. There should be no leakage at all, but this is not practical in real terms. Components such as RF coupling, capacitors, antenna matching transformers allow some current to flow. Underwriter Laboratories has established guidelines for safe leakage currents. The maximum Underwriter Laboratories allowable limit since 1972 is 500 microamps. 500 microamps. That's half a milliamp. Half a milliamp. Consumer electronic devices manufactured before 72 are allowed 750 microamps. The leakage test on the PR95 is calibrated in microamps to compare to the appropriate standard. So those are the numbers we got to think of. 500 is easy to remember. 500 microamps. I wonder if it's marked on here. I'm looking at the microamp scale. There's no marking. There's no. You know what? There is. But it's actually a different scale. But there's a red area on there. It's just my meter telling me I've left it on. Okay, very good. Measuring the leakage at lower levels. Some equipment must be kept at a leakage current which is considerably less than consumer products. Equipment such as clinical hospital equipment requires more resolution than provided by that meter. Simply place an AC meter, blah, 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 blah. Checking the calibration of the leakage test. The current limiting resistor in the safety leakage probe is also a calibration resistor. The calibration of the PR57 leakage test can be done at any time so you know the readings obtained in the test are correct. Am I reading this too fast? The test of the calibration of the leakage. Now plug it into a properly grounded 3-wire AC outlet. Well, I'm in trouble already. I can't do this because I do not have it in a proper grounded. I'd have to. Yeah, it's too much trouble fiddling around with that. So we can't do that. Testing leakage on 3-wire units. Designed to operate exactly the same. Won't worry about this. I don't have a 3-wire unit here. This is a non-polarized 2-prong plug. This thing is what I'm testing is old enough they're not even commenting on it in here. because they mentioned the wide prong, but they never mentioned the unpolarized plug. Testing a line cord and extension cord for leakage. Well, that's interesting. An increasingly common cause of electrical fires is leakage between the conductors of line cords and extension cords. Really? Leakage of this type may eventually short and cause sparks, which may initiate a fire. The instrument used to test for leakage of line cords is your okay, I don't have a Z meter. They're trying to sell another meter to me. Okay, never bought a meter from them in the first place. I think we're ready to go. I'm going to take a little break. We're going to get the probe out and we're going to do these tests. So even though I've mentioned that this isolation transformer is also plugged into another isolation transformer, don't ask me why I did that. I don't know. Because I even have another isolation transformer hidden back here. Lots of isolation. So here's the probe. Single point, just a single conductor. There's nothing to it. There's the button. Push to read the true leakage current. So now I understand why this is here. Because it could be I'm going to put this on 120 volts unexpectedly, and the meter has to be ready for that. Plug it in there. Now, I don't think we'd have this like this anymore. I got to plug this in. What am I plugging it into? I am plugging it into here. But this cord runs all the way around through my little switch panel and down to this extension cord. But basically I'm plugging it in there. And I could actually plug it right in there, but I'm going to plug it in here. That way we can read the voltage here too if we want. Don't think this meter is important right now, so I'm going to get it out of here. So if you look over at the Sencor device, you'll see on here this red band. Now the red band's actually on a different scale. It's for other purposes, I guess. But it almost matches up with the 500 microamps, which is right above where my finger is. So basically, stay out of the red. We should be okay. On a real reading when this is pushed. Get these clip leads out of here too. Okay, I think we're ready. Plugged in. The switch is on. And any reason for me to be anxious? Oh, of course there is. Here we go. So first we'll put this on here. It said it should be done at 117 volts. So we'll see what we end up with here. This is on the end of an extension cord and a few outlets through my switch panel, so the odd volt disappears along the way. 117 to get a calibrated result. Like if you really don't want a calibrated result, close to 117 will do it. So very low. Oh, you know why? I've got it going through those light bulbs. That's why. That's why. 110, so a little higher. Digital stuff. You have to wait. There we are. So that's 117 there. Good. Good. Radar's working. So now I have that resistor connected. So there's going to be a leakage current through the resistor. So let's see what this shows. So I'm going to push over here. High side. Leakage test. I'm not pushing the probe button. Anybody see anything happen here? I don't see anything happening at all. Low side. Goes right over. It's indicating that this is potentially directly connected. Really? It's not so. No, it's not supposed to be. Now, if I push this button, it's already showing too much here. Well, what wasn't there? The idea is you don't push the button if the meter goes all the way over. Wouldn't that be the case? So this is screaming danger, danger, danger. That's what this is screaming out, because it's going way above the 500. It's going right up to the top here. And that's uncalibrated. If I push this button, whack! I don't want to do that. Let's try the high side where I got the low reading. Nothing. I'm going to push the button now and take another reading. That's nothing. I don't think that's surprising. I think it's only going to find it on one side. So Probably this is because of the 220 resistor. And to cut the 220 resistor out, only the capacitor will exist. Then we're going to see some leakage through the capacitor. I wonder if you can actually test capacitors with this thing in some way, like right on your bench. Okay, I'm going to cut that resistor out. Very close to shorting against another terminal, but it didn't. Okay, I'm going to cut the resistor. I'm going to move it out of the way a little bit. Good. Can't reconnect. So now the resistor's gone. The only thing connecting the chassis to the radio's B- bus, if you like, is this capacitor. So anything we measure has to do with that capacitor now. Okay, let's go again. Conceivably the radio's safer now from shock hazard because I've gotten rid of the resistor and the capacitor clearly is less leaky than the resistor current. Clearly? I don't know about that. Maybe I said something wrong there. Okay, so we'll start high side where we got no reading last time. Still no reading. Push the button. Nothing. Other side. Yeah, you know, high side, low side, it's just one side and the other side, I think is really my situation. Here we go. Still goes right over just like it did. Question, am I doing something wrong? Or now it's showing that that capacitor will leak. I mean, I haven't even pushed this button. That capacitor will leak way beyond the 500 microamps that is suggested. Now we're going to disconnect that capacitor. You know, I did that on a lower voltage here too. We'll disconnect the capacitor. Oh, I have to desolder it. I'm one of these guys who likes to see for myself. When I was doing the corrosion work at the power company, this is really obscure work. They handed me a book written in the early 50s and said, here you go. Nobody around me knew anything of what I was doing. I read this book, got the idea. It's very interesting. It's very interesting corrosion effects due to streetcar systems and subway systems. Very interesting stuff. Read it all, and then I said, okay, I see what the book says. The book was written in the 50s. What's happening in the city of Toronto? And I went out to locations that I thought, according to the book, should result in tests, should provide test results that match the book. I go out to the location, try to find a simple area on the streetcar system, do the test, doesn't match the book. I eventually found out why. I won't go into it. Maybe someday I'll do a little talk on underground corrosion and due to stray traction current. That's really what it was. Okay. What did I do here? I lost track of what I did. I turned the radio off so I could desolder this capacitor again and disconnect it. So now there should be no connection between, hey, we can do this test here. We can do this test. Radio switched on and we're supposed to short those together. It probably doesn't really need to be done, but let's do it. So first time we did this one, I just simply read the, just go on there. I read the resistance of the resistor, which is currently cut from the circuit. Resistor and capacitor cut from the circuit. So we want to read the resistance here. I'm going to use this meter to do it. So the point of talking about the corrosion thing was it's an example of just how I like to do things. I just like to find out for myself. I have to go and see it for myself. I don't think I'm alone in that at all. So I want to read the resistance now between the chassis, which should be disconnected, and the power cord. Power cord representing everything inside here. So basically, is anything inside here somehow feeding current into the chassis still? Here we go. Okay. is open. I'm going to put this right up at its maximum, 60 megohms. That's a huge resistance. So this suggests complete isolation now of the chassis from the radio inside. The problem with that is if you operate this radio, this chassis is going to be picking up signals, not just from, you know, stuff, but actually from the radio itself, and convey them around, feed them back into other circuits and coils and stuff, along with picking up all kinds of noise, all kinds of stuff. Which, I mean, you don't want some noisy piece of metal laid up against your radio, right? So that's what this capacitor is all about. It's all about grabbing that and nullifying it. So what we want to do now is do the same thing with this hypersensitive meter. Because compared to this one here, I think the test meter, this meter, far more sensitive. Okay, so we're going to go in here. Now I may have rotated this, so this may change things. Not paying close attention to that. Should it change things? Not really, because this is isolated. There is no ground. There is no this or that. It's kind of the same thing either way, I think. So we're plugged in. We're going to put the power on now. Power is on. I'm going to give it the full power. Hey, we can play the radio, and does it play any different? Am I full of crap when I say these things? I'd like to know if I'm full of crap. That didn't sound very good. Look at that's the kind of stuff that starts happening. So I have a hum signal in me, and when I touch the radio, I share my signal with the chassis. I'm physically a lot bigger here. I'm a better antenna. So that's what happens when you don't have those capacitors in. Now, you might say, don't touch that, you're going to get a shock. I'm not going to get a shock, because I'm operating in an ungrounded arrangement here. I'm not grounded myself. I'm standing, I got rubber-soled shoes on and whatnot. I'm not grounded. So I'm not going to get a shock by touching that. Okay, leakage current. Well, let's find now what I'll do is I'll do this test and find out if I should have just killed myself. Kind of dumb I didn't do it with this first, but I'm pretty sure what I'm doing. That's danger, man. Oh. That's funny. Let's turn down a bit. Wow! Doesn't that do something? Now we can see the current coming up here. High side, or one side. I'll turn this down a little lower. 200 microamps. Other side. Not pushing. I didn't push the button, so I'm not calibrated. It's probably because I reversed this. Because last time around we got a high thing on the low side. High thing on the low side. Let's reverse it. Same test. So I say it just kind of flipped it around, eh? Track of what I was doing. Was I supposed to disconnect that? Now this is this side. It actually is coming up ever so slightly. Is it? Okay, I'm going to push the button. I'm not sure this button does anything. Let's go back to here. Okay, I can afford to push it here. See, I think this button doesn't do a thing. Maybe this button, it doesn't feel like it does anything. How are you supposed to know that? Well, I'm supposed to be cutting, shorting out a resistor, so probably if I read the resistance from here to the other end of the probe and push the button, I'll find out. I'm going to find out. Because if the equipment's not doing what it's supposed to do, then I'm going to get some test results here at some point. That's going to lead to me being embarrassed because test results are bogus. Okay, so we're going to put this at, say 60,000 ohm scale. Let's turn this off. I'm going to leave this operating while I'm fooling around here. I'm liable to forget. Does the little button work? Is there really a resistor in there and we can measure it? It says open circuit. 6 million. There we are. So it's a 135,000 ohm resistor, and if I push this button it should disappear. Yeah, this button doesn't work. You can never get a real reading out of this thing. Ooh! Well, I'm probably just losing connection here. Hold it a little harder. No, see, it doesn't do a thing. And it really looks like you can't take this apart. Although it has a hex arrangement there. Cord's a little loose. Wow, it doesn't look to me like the kind of thing that can come apart. I'll break it, but I'm going to put a little pressure on this and see what happens here. Use my big, this interesting tool. The jaws remain parallel all the time. And that's a beastly cutter there, boy. Powerful thing now. It's turning. Doesn't feel like it's getting loose though. Maybe it's a pressure fit. I may do this. No. No, keep screwing it. It's screwed on. It's screwed on. It is screwed on. Come on out of there. Oh my gosh, there's a little circuit board shoved in here. I think I can grab it and pull it out. How's that going to affect the switch here? Well, it's not working now, so let's pull it out. Come on. Came part way. Somebody just hung up on something? They must have shoved it in there to get it in there. Cord's still loose. Don't break it. Of course, I'm way far away from working on this radio now. I cannot get it out. But you know what you could do, for crying out loud. For crying out loud, that's something my parents said to me all the time. For crying out loud, Jim. So this becomes the resistored probe. That's all. That's just a spring-loaded contact at the top there. This becomes the resistored probe, and just any straight piece of wire is the alternative to using this. So if I just made a straight piece of wire, maybe find an old probe, put this kind of plug on the end of it. Now I got two probes. I got the protected probe with the resistor, unless I busted it here. And I'd have the direct probe I could make the readings with. Or just keep in mind, oh my gosh, how do you avoid cross-threading this? Okay, so what I usually do is I turn things backwards till they click. Or you feel it. Yeah, I don't know. Yeah, I don't know. Turn it forwards. That's good. That's got it. You know, this tool has a little slot in the head there. That's for holding like a piece, something round. It's quite the tool. It's a beastly guy. Must have a manufacturer's name on it somewhere. Looks like it might be worn off of here. This has been used so much. The knurling, here it is. Bernard. Mr. Bernard made this. Yeah, it says Bernard there too. Oh, it says something here. So this could be 100 years old. I don't really know how old this is. It's probably from the 1950s though. And my little magnifying glass. So made in the USA, New Haven, Wisconsin, New Haven, Connecticut, by the Skollhorn Company. W.S. Skollhorn, or something like that. W. Skollhorn Company. Wow. Bet you can't buy one of those today. Oh, you probably can. You probably buy a better one and try. Okay, let me put away my great tool. That was my father-in-law's tool. He was a machinist, working in a small remote town with a paper mill way up north in Ontario. He was their master machinist. Okay, what have we found out here? Found out the probe doesn't work, and I've always been suspicious about that. We found out when we make a reading with this probe, the resistor's in place, and we're getting a low current reading over here. The meter's designed so that if there's a full voltage on here, then it will go high right to the top nicely without the button pushed. Pushing the button doesn't do anything anyway, so we saw that happen. I disconnected the resistor and the capacitor, and we saw no significant leakage current. Is that right? Was that right? No significant leakage current. I'm going to do it again. Too much stuff jumbled up in my head, and sometimes that's okay. That can be quite okay. You don't need to have everything straightened out. Other times, maybe you do gotta take some effort to make sure of stuff. Okay, radio is operating. Humming away. Once again, low side. Didn't we get it this time? We hear it, but we don't see it. High side. There's nothing showing up at all. Did I break? No, I didn't break the probe. Oh, it's important to plug the probe in, apparently. You can't really do this with the probe not plugged in. It's interesting though that this made sound. Fool me. Okay, here we go. And the other side. Hoo-yah! We'll check the button again just in case somehow what I did fixed it. Button does nothing at all. The actual amount of current we're reading now, without the capacitor and without the resistor. It's 175 microamps. So somehow 175 microamps makes it from the circuit into this chassis under this test. When there's a resistor here. If the resistor wasn't here, this meter would probably go a lot higher. One could argue that the resistor here is kind of like you. You know, you have a certain resistance. Mine is very low because of the incredible moisture. Oh, I was going to tell you a story too. Incredible moisture on my hands. I get a shock real easy. Is this representing the amount of current that would flow through a human being? I don't think so. I think what would actually flow through me if I set myself up like this meter would be more, but probably not enough for me to feel anything at all. And now my story, and then I'm going to go drink some coffee. So when I was working when I was in college, I worked as a building maintenance guy in the apartment building I lived in. It was actually a housing co-op, student housing co-op. And me and a number of other students were kind of like part-time maintenance guys, and then there was a couple of full-time serious maintenance staff, you know, could do the plumbing, all that kind of stuff. We just did the small stuff. One day I'm in a room, and there's an electrician that was hired by the building to do something. I don't know what he was doing, but maybe replacing outlets. I don't know. There were wires sticking out of the outlets. The outlets had been removed and the wires were sticking out. And he walked over, and not paying too much attention to me, I heard him say, "Geez, are these live?" And so I looked over and I watched him, reach down and grab the white and black wires like that and hold them. And he went, no, I don't think it's live. And he let go. I almost fell over. I mean, I'm studying electronics, and that looks like a suicide move to me. So I come over to him. I say, what are you doing? Maybe I wasn't quite that excited. Excuse me, sir. Well, what did you just do there? And he explained to me. His hands were so dry. He showed them to me. They were dry as could be. You could see he had dry hands. He goes, my hands are so dry, I don't conduct. So I just grab it. You know, if they were live, I feel a little bit. If I did that, I think I wouldn't be here now. Wow. So, how much electricity does it take to kill you? That guy a lot. But for most people, no, not a lot. Yeah, I said I was going to have a coffee now and calm myself down, so get back to doing something with the radio. Since this whole leakage thing is clearly the topic for my video today, let's go further. This document, after reading through it, is really designed to try to sell this device, of course, but nevertheless it does contain some information about, there, look, he's pushing the button. He's pushing the button. Hey, the button doesn't work, buddy. He doesn't know that. Let's read this part here. What causes leakage? Because I am reading a leakage current with this device on a radio I've left on here. I better turn it off. And the leak can't be from the resistor or capacitor that tie to the chassis. So what is leaking? Where can a leak be? Here, they're going to give us some ideas. So I'm just going to read through this, not quite as fast as I was reading earlier. Basically, any path that will place the customer in either direct or indirect contact with the AC line is dangerous. There are many ways in which this can happen. The following is a list of some of the most common causes of leakage. Leakage to the chassis. Shorted antenna bypass capacitors. You may see a lot of shorted antenna bypass capacitors after a thunderstorm. The capacitors are in series with the antenna terminals and the chassis to isolate the hot chassis from the antenna. Did you get that? Let me just repeat that. The capacitors are in series between the antenna terminals and the chassis to isolate the hot chassis from the antenna. Because people are going to handle the antenna. And almost certainly the antenna is going to be a bare wire. And they're going to be in their backyard walking around with wet running shoes on their lawn. And they're ready to get killed. So there's a capacitor in there to limit the current that they might experience, and at the same time allowing the antenna signal to reach the radio. That's what that capacitor is there for. When one of these capacitors is shorted, the customer notices no difference in the operation of their receiver because the RF signal passes through the shorted capacitor just as well as through the good capacitor. The problem, however, is the antenna terminals now have raw AC on them. Raw AC. Improperly installed tuner. Occasionally, replacement tuners are installed improperly or with the wrong kind. Or with the wrong kind. Isolation capacitors must be installed properly to avoid the AC line from being tied to exposed metal parts. Also, insulated shafts on tuners should be replaced with a similar kind to avoid a shock hazard on the tuning knob. Yeah. Conductive knobs. If the TV being serviced, it's a television set, has control shafts that are connected directly to a hot chassis. Televisions had hot chassis? Or accidentally hot chassis. Like radios had purposeful hot chassis. But televisions, I don't think they ever did, because they have a big transformer in them. Knobs on these shafts must be insulating knobs. Many times, however, knobs that have been replaced are metal or chrome plated, which may conduct current. Well, this isn't where the leak comes from. They're telling you where the leak's going. It's going how it's going in your end. Defective isolation transformers. Older TV receivers often have built-in. Hey, that's describing me. Built-in isolation transformers that are supposed to isolate the metal chassis from the AC line. But these older transformers occasionally develop leakage between the primary and secondary windings, causing a hot chassis. This is especially dangerous on the older sets with metal cases or with metal pans covering the bottom of the chassis. All of the exposed metal becomes a shock hazard. AC bypass capacitors. These capacitors connect between the AC line and the chassis. Now this is the capacitor I'm dealing with. Would be called an AC, I guess could be called an AC bypass capacitor. These capacitors connect between the AC line and the chassis in most electronic devices that use isolation transformers. Well, okay, so this device does not have a transformer. The capacitors bypass RF interference picked up by the metal chassis to the AC line for shielding purposes. That's kind of a weird way to describe it. Why is the print going up and down in size in this document? Older capacitors were often wax-coated paper type, which often developed leakage as the paper dielectric absorbed moisture. Exactly right. In some cases, a capacitor shorts completely, causing a direct connection between the AC line and the chassis. Danger, danger, danger! These capacitors, like antennas, These capacitors, like antenna bypass capacitors, are commonly damaged during thunderstorms. That's interesting. You know, your antenna, your house, your antenna, your stuff doesn't have to be hit by the bolt directly. The bolt can hit the ground some distance away. This causes a huge rise in the ground potential. That huge rise in the ground potential rolls off as you get farther and farther away from the bolt. There can be pieces of underground metal or metal that are in the elevated area, but those pieces of metal, such as the hydroneutral and that, remain at the same potential they always did. So now they are running in ground that has gone up in potential. So you could be standing on that ground that's been raised shockingly by a bolt of lightning, you know, some hundreds of feet away. And you can get electrocuted because you're holding on to the hydroneutral, which hasn't raised in potential, but the ground you're standing on has. Those things are called step and touch potentials, and they're well known. If you work in this industry, you know what step and touch potentials are. But would you believe this? If you walk up to a hydro tower in a park, let's say, where you can walk up to it, often there's a fence around the tower, and that's mostly to keep children from climbing the towers. If you look at the fence, you'll see a lot of copper, big copper cables attached to it, usually on the piping of the fence, a stainless or a chain link fence. You might even find the odd ground rod if you look really hard, but the fence itself is acting as a grounding terminal. So the fence is bonded to the hydro tower. And the reason for this is to make sure there's no voltage difference between the tower and the fence, because guys go inside there to work and they don't want to touch a fence that's grounded and touch a tower that's at a different voltage and get a shock off it. And you're talking, hydro tower, you know what kind of shocks you get? Deadly shocks for sure. So all this stuff is tied together. It's called bonding. So the fence and the tower are the same voltage all the time. So there's no voltage difference, can't get a shock. That's called kind of touch potential. But now you've introduced something called step potential. Step potential, picture yourself standing outside the fence, maybe looking up at the beautiful tower and appreciating the wonderful history of electrical distribution. And you happen to lean onto the fence. So you're standing about a meter away from the fence, and you put your hand on the fence. Nothing will happen. You'll be just fine. Unless, at that moment, one of those big high tension wires should snap, fall down, and touch the tower. Touches the tower for some period of time, we're talking a fraction of a second, but maybe longer. The tower will rise up to the voltage of that cable. Well, those cables, they can have, 250,000 volts on them or something like that. So some huge voltage will be stuck on that tower briefly, and therefore on the fence, because they're wired together with big bonding cables, and therefore on your hand. So now you've got your hand on a tower. It's really sad that you happen to do that at the moment this wire came down. So it's not very likely, is it? But your hand's on it. Your feet are a meter away from the fence. There's a potential gradient in the ground. The voltage is rolling off as you move away from the base of the fence. So how much voltage would be there? In Canada, touch voltages in those situations are expected to reach 8,000 volts. The theory is they last for such a short period that it would not kill anybody. To make it lower costs a lot more money. What you could do is you could extend wires under the ground around the outside of the fence. Buried ground wires, maybe going 2-3 meters, far enough away that you can stand there, you can't touch the fence anymore. And if you did, it didn't matter because the ground is now being lifted up also. The ground you're standing on is being lifted up to 8,000 volts or whatever. You won't get a shock. So step potential is you're standing outside the fence and your feet are apart about 1 meter. Now you're standing in such a way that when the wire falls on the tower and the disaster happens, a voltage exists between your feet in the ground. So that's called step potential, and that's also studied and controlled and engineered. The last one, this one is not talked about very much. It's called a dog on a chain. So the idea of the dog on a chain is somebody's walking their dog and they're using a metal chain. Now, who does that? Nobody does that. But let's say you did. So your dog could be 20 feet away from you. That's an awfully long metal chain, isn't it? Okay, 5 feet away from you. And you are electrically connected through the dog, through the chain. So now you got dog potential. I don't know what to call it. Dog on a chain problem. I don't think that was ever engineered. I don't think anybody ever really, did anything about it. Nobody. I mean, what kind of dog have you got that you need a chain? Maybe you shouldn't have that dog in the first place. So these are all issues around getting shocks because things are getting electrified by accident, and that's kind of what we're talking about with this radio. Let's keep going here. I kind of lost track of where I was. Installed tuner, it didn't make much sense to me. AC bypass capacitors, older capacitors, completely. Did I reach the end of this already? Oh, I started explaining why a thunderstorm some distance from you can cause capacitors in your antenna to blow. That's called, I think it's called communicated voltage. So the idea is you have, just picture a pipe in the ground. Just a steel pipe, like a water pipe. And, it's a big heavy steel pipe, so current flowing on it doesn't cause much of a voltage drop. Let's just assume that. And that pipe runs, through your neighborhood out into the other neighborhood. The other neighborhood gets hit by lightning. The pipe in that area, actually I got this backwards. I got this kind of backwards. I guess it could work either way. Let's keep going with what I'm saying. So the lightning bolt happens in your neighborhood, 150, 200 meters away, striking the ground, not striking a hydro tower or anything, striking the earth, right into the earth. So, you know what, you won't get this, no, this story doesn't work. It's the other way around. It's that you are standing in the area that the lightning bolt raised the ground potential briefly, and in that same area is water pipes that extend way out. Of course, water pipes go for miles and miles. So the potential of the water pipe doesn't change. Now it's sticking in ground at a high potential, earth at a high potential. So you're holding the water pipe and you're standing on the ground. The bolt of lightning hits a couple hundred meters away and you get a shock. That's kind of how I would view this. You ever watch videos of people getting hit by lightning? It's really ugly. It's really ugly. So we don't get hit by lightning. Okay, we're up here now. Bent rabbit ears. Why? Many receivers have rabbit ear antennas designed to slide down the back of the case. Generally, there is a plastic tube inside the case to isolate the metal antenna rods from the chassis. But the rods often get bent, and the rods are bent. When the bent rods are pushed down into the nested position, they touch the hot chassis. Yeah, this probably happened. Improper installation of parts. Forgetting to replace an insulating piece of fish paper. Fish paper. I've got fish knives. I don't have any fish paper. Never heard that term before, but I think we know what they're talking about. So you've got a, like I'm working on the radio here, and I don't pay close attention, and somehow I accidentally drip into place a solder connection from the terminal down to the chassis, and I don't see the drip. That's kind of what they're talking about here, sort of. Foreign objects touching the AC line, allowing a piece of wire or solder, there you are, or solder to fall between one side of the AC line and the chassis. Well, this is exactly what I just talked about. Broken safety ground. The broken ground may allow a shaft or control to float. So I wouldn't use the word ground here. I would use the word bond wire myself because of my background in the electric industry. I'd say, so we have a shaft that's bonded and the bond is broken. So the reason you use the word bond is because it comes along with an understanding of why it's there. If you just say wire, that doesn't help. You say ground, it's very vague. So say bond, and you know, oh, that's a wire put between two pieces of non-current carrying metal to make sure they don't have a difference in potential in case you touch them both at the same time and that wire hits the tower, you know. Using long metal screws. Well, this one has concerned me. Putting things back together and putting a screw in, and is this the right screw? I don't know. I'll put it in. Hey, it went in fine, but it went in way farther than expected and ends up touching something that you don't want it to touch. If you could replace components in a radio, you can accidentally put one right where the screw is going to go. Didn't we have a radio like that? Just that somebody had driven a screw into the filter capacitor in the radio. But I don't think it actually shorted it out, but boy, was it close. Yeah, that was just a couple of radios ago I saw that. Adding an earpiece or accessory jacks. You know what? Don't do this to radios that are AC/DC radios or radios without a transformer. That's my opinion. Do whatever you want in your life. It's all your choice. But personally, I discourage people from doing this. Find a radio that's got a phono jack on it already. Find a radio with a big power transformer. If you want an old radio to play your Bluetooth through, do that. Don't do these 5-tube no transformer radios, even if you have the power right test equipment. Is that the end of the list? Foreign objects. Coins, hairpins, or other metal objects which have fallen inside the set. Of course, in our case, when we're working here, if we cut a wire, the little wire chip can fall into the set and disappear, and you think you found it when you didn't, and forget about it, and next thing you know, it's a short. Could be a short to the chassis. Connecting an external speaker. Wiring accessories to a set that do not have an isolation transformer. If you remember the schematic, here, let's flip to it. The schematic shows this on the speaker. The speaker frame, well, it's bolted. You know, this is probably what this represents. The speaker frame is bolted to the chassis. So the speaker frame is also doing whatever the chassis is doing. So that's why I take a look in these schematics. I look to see what's going on with the grounding of the speaker, according to the schematic. The list could go on and on. The key thing is there is a shock hazard anytime a piece of metal comes in contact with a hot chassis. I won't read this, but look, it's fast and simple. Okay, really? I spent all morning on this. I think that's great, though. I think we're... Now, what are we going to do about that radio? Okay, interesting question. Is there some way I can discover where the leak is coming from in here? Oh my gosh. Probably no. Is it worth giving it a shot? Why not? I've done all this today with this thing. Let's do some more with it. So I'm going to put the power back on. Now, most of the metal in here is all tied together. So a test here, and a test here, and a test here, and a test on the speaker. It's all the same test. Test on this clip. It's all the same. Now, an interesting thing is the shell of this switch. And you have the power cord coming right here. It's a short distance from there to there. Oh my gosh, it's really close. Yeah, close, but it's not going to short. Now, wait a minute. I don't have the capacitor connected, and I don't have the resistor connected. That's okay. Let's start with the chassis, watching the meter over yonder. Okay, same sort of deal as last time. So I just touch different pieces of metal, see if by some chance something different happens. I mean, this is all bolted in there. Where is there something that's not really bolted in? There's nothing. Nothing, and there should be nothing. There should be nothing at all that is floating free here. Yeah, I don't think it's possible for me to determine. Something is supplying the current to make that happen. Somehow. I just don't know how you would I don't know how you would approach it. What if we touch non-conductive surfaces with this? What if I do something stupid like this? This is a microamp meter, so it's pretty sensitive. Be careful, don't short that out. You might think this is crazy what I'm doing, but it's not that crazy. See this black material here? This black paint? I have a desk that all my old radios are on, where I listen to my really old guys. It has this kind of black surface. You've seen it. This kind of desk's common. It's a corner desk, you know, classic. Buy it for your kid so he can do his math on it type desk. This surface is completely conductive. Not this one. Well, I don't know about this one. I don't think so. But that desk is completely conductive. It's dangerous for the kind of things I do because I'm touching it all the time, and I have equipment sitting on it. It's yeah. So you would never think it's conductive looking at it. You would never think this is conductive. Is it? I'm sure it's not. We'll flip this on. No. But if I did this here, you see it jump there for a minute? I have found conductive spots on my desk here. Not with this though. Not with this meter. Okay, it looked like a fool. That's the show me thing. Better show me that. So we can't really figure out what it is that's leaking. The leak is very, very small. The leak could be from 16 different things all leaking a little bit of current here and there. Who knows? So, leaving that out of the picture now, what do we do with this radio? It's pretty simple. We just reattach the resistor there, which is fine. Change this capacitor, even though it appears to be pretty good. We can do this. We can do this. Okay, watch that meter, and I'm gonna push this capacitor back on. Ooh, now what does that tell you? I think that pretty much proves that capacitor is leaking that kind of current. With the resistor disconnected. Okay, let's put a new capacitor in there, leave the resistor disconnected, and see what happens with the new capacitor. I have special capacitors for this purpose. I'm going to pick one and stick it in there. And how big was this guy? It's physically very large. Let me just peek at the schematic here on my own to remind myself. 0.2. A big fat 0.2. Okay, we'll stick one in there. Okay, just thinking a bit further. Before I stick a new capacitor in here, let's pull this guy out. Look how much lead there is on this thing. They just kind of jammed in there instead of shortening it up. And I'm going to go down here. Cut this guy here. Here he is. 0.2 right there. And the voltage, I can't see it. I can't really read it, but it's going to be, looks like 400 volt. Okay, I'll find a 0.2 we can stick in there. Oh, let's test this thing. Yeah, let's test this thing. Think about how can you use this to test this. But let's use the tester I'm familiar with, and I know how to interpret it. That's this guy here. Hey, bird, out of the way. You might say, why do you have glass birds in your shop? And I might say, because. That's about the best answer I can give to that. Okay, we're going to hook up the capacitor. We already know this guy is leaking enough to show up on those test results. Big capacitor, 50 volts. What do you say? You give it some time now because it takes time to charge. So the pie is just on the verge of opening a bit here. Very leaky capacitor. That's what this would amount to. And we'll grab the safety capacitors down here. There's some here. Now, 0.2, that's a big one. This is a 0.1. I don't know if I have a 0.2. Well, let's test this. Brand new capacitor. And what's the volt? These things are sometimes their voltage rating is very low on these guys. Voltage rating here is 275 volts AC. Could probably take 400 DC. $50 volts, watching the eye. Boom, right open. 150, right open. 250, right. I mean, it's just going to go. If we could go up to 450, it would go right open. So just to keep me honest, is one of these going to be enough? It's a 0.2 in there to start with. Yeah, I have two like this, but wow, these are expensive. These are expensive capacitors. Okay, I'm going to look around and see what I can find. And let's see. Okay, we're back here at the tester again. So there's no doubt this is a totally good, brand new capacitor. I checked the reading on it. It's a 0.1 for sure. It reads what it says on it, 0.1. But I'm looking for a 0.2. Don't have one like this, 0.2. I got this. This old looking thing, really dirty in that, but in fact I think it was just in somebody's just in dirty environments. It's never been in a radio. It's got its entire leads. It's basically NOS, new old stock. I tested this one for its capacitance using the using this amazing little device here, and it's correct. It reads 0.22. It's 0.22. Let's put the leakage test to it. Let's see what happens. This is a monster of a capacitor, though. Wow. Really well sealed. Let's see if it's good. There we go. Takes time to charge. Okay, I don't think it opened all the way. 150. No. In this position, we're trying to put a capacitor in that has no leak in it. This guy's leaky. Can't use it in this spot. It's self-defeating in a sense. So I'm going to put in a 0.1, and I'll bet you we'll have no trouble with that, and everything will be fine and happy. And this is a proper kind of capacitor to put in that kind of position. Not so critical in this radio, frankly. In other radios, a capacitor like this goes right across the power line. In some, I had one in here just the other day, capacitor in that position, right across the power line, ahead of the switch. So it was always on the power. Power was always on to it anytime the radio was plugged in. Ooh, that's bad. I don't like that. That thing can give out in the middle of the night. So we're going to put this guy in here. And we're going to test the radio with the resistor still open so I can see the effect of this capacitor. And we also want to do it so I can have it not connected and push it into a connection. We can listen to the effect. Nah, you know what? That's not worth doing. That's not worth doing. So I'm just going to install this capacitor and we will just carry on from there. Okay, I'll get that done. And eventually I'll put that resistor or another one back in too. Okay, so just to be clear, the main thing I've done is put a new capacitor in this position. I think you could probably use almost any capacitor you really wanted to use as long as it's new. You can tell this one here failed the leakage test, I would think. I will save it. Someday it'll find its way into a radio in a less critical location. So plug the radio in. Once again, don't know that I plugged it in the same way, but I think I did. Last time. Get some stuff off the bench here. Okay. So what's the story now? If there is current leaking onto the chassis, which we believe there is from some unknown location, that current, tiny current, will encounter this capacitor. It's AC current, 60 cycle AC current, and it'll flow through this capacitor to ground. That's one way of looking at it. Another way is this capacitor is forcing the chassis. Hey, what's going on over there? I don't even have this switched on. I don't know what to think. I don't even have it switched on. I don't have it switched on. How does it get a reading like that? Is there a ground connection I don't know about in my own system? It's impossible. Just a metal chassis sitting here on my bench will cause that meter to go over without any supply. Let me grab a nice chunk of metal here. Some metallic thing. Something substantial. Substantial metal thing. Oh, for crying out loud. How about this? How about this? Just a big metal lid here. Just a great big metal lid. What happens if I touch that? Okay, so I have to put this somewhere where it's not in contact, just sitting here. Okay, I don't think it's in contact with anything. Meter, what do you say? Nothing. Certainly not surprised by that. Well, it's coming out of here, Jim, because you pulled that out and it disappeared. It's definitely coming out of here. I don't know what to make of this. Let us go a little further with it. Maybe there's a leakage way back in here somewhere in my somewhat circuitous setup. Maybe that's somehow being brought forward to the chassis now, and I'm able to catch it with this. Yikes! I don't like it when stuff like that happens. I don't think it's of any consequence whatsoever, but I don't like it. Okay, so now we're plugged in, but the switch up here is off. So one leg is open. I think this is a double pole switch. So I think both legs are open. Well, I built this a long time ago. Maybe I'm wrong. Okay, so here goes the power on. Here we go. Power on. Where'd it go? A little tiny amount showing up. Showing up through that, maybe. Can you even see the meter moving here? That's with the resistor in. There we go. That's with the resistor in. Let's flip this. Watch this. Up it goes. That's the thing about these radios, is you may think you've solved the hot chassis problem by plugging it in and making a measurement. Okay, it's not hot anymore. Then you turn the set off and look out. The other way around, got the set turned off, move the plug, read the voltage. Good, no voltage anymore. Turn the set on. It's over. It's hard to escape the hot chassis problem. Very hard. Well, but there's no humming. It's too much for my little brain to explain, that's for sure. Okay, we don't have the resistor connected. What is that resistor there for anyway? Like, why have that? So I'm going to try to find that out, and then we'll finish off this video. I'm going to hunt around, find out what that resistor's for. Okay, so reading through one of my books, Elements of Radio Servicing by Marcus and Levy. Great book. There's quite a few versions of this. I've got all the versions of their book. So here we go. I'm going to read this whole section, Floating Chassis Circuits and AC/DC Receivers. I'm going to read this stuff to you. Okay. Here we go. Floating chassis circuits and AC/DC receivers. This is an AC/DC receiver. Early AC/DC receivers connected B- to the receiver chassis, as shown in figure 818. I guess this would be here. Since one side of the lighting mains, this is a British guy, of course, talking, the lighting mains is always grounded, it is desirable that B- be connected to that grounded main. However, if the plug is reversed, they're talking about the plug, the unpolarized plug. I lost where I was. However, if the plug is reversed, B- and therefore the chassis would be connected to the hot side of the line. I have a lot of radios in here that are like this. The chassis is connected right to one of these two wires. Various disadvantages would result from this. Floating the chassis. First, the antenna may become grounded. An outdoor antenna or lead-in wire may ground on some grounded object. Some installations use a steam radiator antenna. I don't know how many people have steam radiators in their houses anymore, but steam radiator antenna, which is grounded through the water mains. All AC/DC receivers use a small condenser, capacitor, in series with the antenna circuit to isolate the antenna and to avoid the possible short circuits resulting from a grounded antenna. However, if the capacitor were to short, then the grounded antenna would be connected to the hot side of the line and it would short circuit the power mains. Or, if the insulation of the antenna wire were to become frayed as it goes through the chassis and make contact between the wire and the chassis, it would connect the chassis ground to the grounded antenna, again resulting in a short right across the mains. Another way in which the chassis may become grounded is connected with the portability of small AC/DC receivers. People carry receivers of this type from room to room in their homes and set them down in any convenient spot, plug in, and enjoy their favorite programs. If the convenient spot turns out to be a steam radiator, that's good. I guess in the summer you could put it on your steam radiator. There is a likelihood of a short circuit through the chassis holding bolts, which extend through the bottom of the cabinet. This problem of a possible short circuit of the lighting mains through the chassis does not occur with AC receivers. What they mean when they say AC receivers, I mean radios with a power transformer. Does not occur with AC receivers since the power transformer automatically insulates, I would use the word isolates, B- and the chassis from any direct contact with the line. In AC/DC receivers like this one, B- must be connected to one side of the line. Well, many modern AC/DC, many modern AC/DC receivers avoid, why are they called AC/DC? I believe there was some DC power still available and some people had DC power in their homes, and so they could plug this radio into DC power and it would still work as long as it was the right voltage, I think. Avoid the possibility. Okay, because there's no transformer. Who needs AC, right? Many modern AC/DC receivers avoid the possibility of short-circuiting the line through the chassis by floating it. Now that's what's gone on here. That is, insulating the chassis from B- and consequently the line. That's how this has been made. A receiver of this type is the Motorola so-and-so. Okay, the line switch connects to B-. I'm not sure what. So they're going to talk about this right now. Let's just go through it. May not understand this. Note the use of the special symbol that denotes B-. This makes the diagram easier to read. So many circuits are going to be. The chassis is connected to B- through a 0.25 microfarad capacitor. That's this thing. Near the line switch. Since this condenser offers practically no impedance to RF currents, it permits many components to be grounded to the chassis and still act as if they are grounded. What? It permits many components to be connected to the chassis and still act as if they are grounded. I don't get that. Since this condenser offers practically no impedance to RF. Oh, I see what it's saying. I wish they wouldn't use the word grounded. These components are the rotor of the gang tuning condenser, the tube and coil shields, and the antenna coil primary. Yeah, often in a radio you'll see that these things are tied to the chassis, but nothing else is, except through the capacitor. The B minus is through the capacitor. These components, its impedance is high with regard to low frequencies and therefore serves to isolate B minus from the chassis for them. And the low frequency they're talking about is 60 cycles of power coming in. So 60 cycles sees this as a resistor. It's not quite true, but you can think of it that way. Whereas RF sees it as a short circuit. So consequently, any RF that's floating around in the chassis and that is delivered back to the B minus where it is essentially killed. We'll use that word. And here's all the checks here. Normal test data for AC power supply. That's different. They're talking about the power supply in general. So that's what this book says about that capacitor. Two kinds of radios. Earlier radios, chassis connected directly to B minus, steps taken to make sure you can't touch the chassis. Some of those radios, like these knobs, they do not protrude past the plastic cabinet. They are recessed in the cabinet. If you pull the plastic knob off, the metal part is recessed in the cabinet. The idea is you can't touch it. You have to stick your finger in, you can still touch it. And those knobs, I'm trying to find one. I don't have any knobs floating around in here. Unlike this knob, they extend out. So they can reach into the chassis hole where this is hidden. You reach in. That's one. So that would, if you have a radio like that, you pull the knob off. It has a long collar going in, and this is recessed. That's a hint. Total hot chassis, B minus right on the chassis. And I have had radios like that for sure. Then later on, they figured out that that's just too much trouble. Why don't we just try isolating away the chassis? We'll put a wire in for B minus and run it around in here and make connections. And the problem with that, of course, is the chassis then is a free floating piece of metal. So let's ground it, although that's a bad term. Let's just tie it back to B minus, and then it won't have any influence on the radio's operation. We tie it back with a capacitor that will allow RF to whip through it, but won't allow a AC current to flow through it easily. I'm looking at the antenna. See that capacitor on the antenna? So look. So it goes from here to here. What's this? This is this green wire. What's this? This is the antenna wire. So if you want to extend a wire out, there's a capacitor sitting here protecting you and the radio in Niagara Falls. The Sir Adam Beck generator at Niagara Falls. All protected by that. I wouldn't recommend people put a wire antenna on these radios. The loop antenna is the best way to go for sure. Putting a wire antenna on it, you're just going to get a bunch of noise in the radio, I think. Okay. Where are we at now? Where are we at with this thing? We have that resistor. Oh, I was trying to find out the purpose of the resistor. Never found that out. Jeepers. Well, I'm not finding any reference to the resistor. But I did find a very interesting section in this book. This is the same author, twice as many pages. Marcus did this book. I thought it was Levy. Okay. So let's read this. AC/DC power supply. So this is an AC/DC radio. Up here you could plug it into a DC power, but nobody has that. This is interesting though. The chances of failure in the AC/DC power supply are greater than in one designed to operate only on alternating current. Since the bulk of the power transformer is eliminated, the tendency is to make the AC/DC receiver as compact as possible. Thus, not only are the various components crowded closer together, but ventilation is poorer as well, and as a result, these components run hotter and are more likely to break down or dry out. Especially is this true, that's a weird way of saying that. Especially is this true where a dropping resistor or ballast tube is employed in the filament circuit. After a short period of operation, these components become very hot, and care must be exercised when probing inside the receiver, else a bad burn may result. If a voltage dropping line cord, did you know that some of these radios, much older radios, the line cord is actually a resistor. It drops the voltage coming to the radio. Did you know that? If you replace the power cord with just your typical power cord, you'll be in trouble. Those are really old radios though. If a voltage dropping line cord is employed, the cord will become quite warm, but the cord is outside the receiver where it can do no harm. Oh yeah? However, care should be taken that this cord is not short-circuited or otherwise damaged by wetting or rough handling. A line cord of this type should never be repaired by cutting off a portion, since its resistance would be decreased and the tubes may burn out as a result. Since the cost of a power transformer is eliminated, the cost of the receiver is reduced appreciably. Thus, the AC/DC receiver may be manufactured to sell at a low cost. In a competitive market, the temptation is very strong to produce less expensive receivers by skimping on the size and quality of the various components. As a result, the inexpensive AC/DC receiver is often manufactured with inferior parts. Accordingly, breakdown is more frequent. I thought that was interesting. Basically, you're looking at cheap radio here. Cheap techniques, cheap, and under the force of competition. Well, I think I've really spent far too much time in here, far too much talking. So I'm going to stop right here. It will connect that resistor back up in there. There's no reason to change it. And we'll carry on. This one I've reconnected already. We'll carry on with whatever's next. What's next? I don't know. We'll see tomorrow. Thanks a lot for watching, and I hope you're getting something out of this. I'm kind of jumping around, and I may be talking about, I don't want to say over a person's head, but there may be things I'm saying that you're not familiar with. Well, ask Mr. Google. In fact, ask Mr. AI your questions. Do that for sure. Thanks a lot for watching, and see you tomorrow.